Hello YouTube. In this video we're going to be covering the special solution cases of solving 2x2 systems of linear only equations. Okay, and these special cases, of which there are three we see here, are the one solution, no solution, and infinitely many solution cases. So we're going to go ahead and take a look at these both algebraically but also graphically, because we want to interpret these things in terms of like number of solutions to a system, and so it helps to see these things graphically, but also know how they behave algebraically if you don't have a graphing utility available to you, or you just simply don't know how to graph them. Let's go ahead and start with this one solution case up here on the top left here. We see we have a system, two equations, two variables, and we could solve this either using elimination or substitution. In this instance, it is actually convenient to use elimination, seeing as how they're both in standard form. That is, we have our x's lined up, y's lined up, but also because we don't have any variables isolated already. So taking a look at this, we'd say, well, why don't we go ahead and distribute a scalar of 2 throughout the second equation here, which produces a new system, and that system would be this. Now, our first constraint, we did not scalar multiply through. Our second constraint, however, we say 2x plus 6y equals 30. So summing these, we see that our x's drop out. We end up with 9 total y's, and then we end up with 36 constants. So I guess it's easy to see here that when we do this, you actually end up with a y value. And I know this sounds silly. When you solve a system, you often end up with a y value. And of course, we could find the x value by plugging this back into one of the original two constraints. Would be very convenient to plug it into the second one since we're solving for x, and x has a coefficient of 1 in the second constraint. So we see that this would produce x plus 3 times blank equals 15, and going in the blank we have this grand 4, and so now we have x plus 12 is 15, and solving for x we have x is 3. So when x is 3, essentially graphically speaking, we'll see that we get a y value 4. This is a point that is on both graphs because it is a solution to both of the equations, and of course a graph is no more than the set of all points that are solutions to an equation. But I do want to point this out because the next two systems we'll go through that have no solutions and infinitely many solutions respectively, you're going to see that necessarily you don't get a y value, nor do you get an x value. But the moment you get either a y or an x, you know that you end up with a system with one solution. And as a matter of fact, before we go ahead and graph this, we're going to give this system a name. It is referred to as a consistent system. Okay, so consistent, the opposite of consistent, of course, would be inconsistent. But what we mean by consistent is simply this. Consistent means that at least there exists a solution to the system. At least it has one. Might as well go ahead and name the no solution case now as inconsistent. There's only one type of inconsistent system, and that would be any system that contains no solutions. But we also refer to this system as consistent independent. Independent. Okay. So let's go ahead and take a look at the graph of the system now. You're going to notice on all three of my systems here, I start with the constraint negative 2x plus 3y equals 6. So looking at this over here now, we say negative 2x plus 3y equals 6 is this line here. Let's go ahead and graph the next constraint, which is x plus 3y equal to 15. Equal to 15. And so you'll notice that it does contain on both graphs the solution point 3, 4. That's why I refer to it as the solution to the system, but also this, that both of these lines did not have the same slope, so that's kind of a big deal. So we're going to draw kind of a rough sketch of what this would necessarily look like underneath our notes here, but we say a one solution system that is consistent independent. Okay, I will get here. There we go. We say has a graph that has a point of intersection between the two lines. So like, something like this. We say one solution, they intersect once, and unequal slopes. Unequal slopes. It's very important. Keep that in mind. Okay. So let's move on to our no solution case. Now, first thing I do want to point out is this. If you have a savvy eye, you would see that one equation on the left here, especially, we say is necessarily a scalar multiple of the other equation. That is, if we were to double the first equation and take it times a negative, you would have 4x and minus 6y, and so it almost very nearly produces the second equation. As a matter of fact, if I was going to solve this system using the elimination method, I would totally take the top equation times this constant, this scalar multiple here. So we say doubling this by a negative, we get 4x minus 6y, and this comes out to be a constant of negative 12 on the right. On the left here, again with our second equation, negative 4x minus 6y equals negative 3. As a matter of fact, sorry, I don't know why I took the top equation times a negative. Let's go ahead and switch their signs back here. We'll take it times a negative 1 again. We're trying to eliminate, aren't we? So our 4x's drop out, but also our y's drop out. So now you've dropped both of your variables. And this is very, very characteristic of a no solution or infinitely many solution case. But in this case, we get 0 equals 9, which of course is not a valid statement. It's an invalid statement. So this should scream at us that this is true never. So we say no solutions, first of all. We have a no solution case. So this is an inconsistent system. Inconsistent in that it has absolutely 0 solutions, not even one. You know, some solutions have one, some have many. Those are both consistent. This one is inconsistent because it has none. And the last thing is this. If we were to graph both of these equations now, so like going back over here to GeoGebra, we take out this second constraint. That's easy to do. And let's drop in the second constraint on this system, which was a positive 4x minus 6y equal to, I believe I had negative 3. You see that we have two parallel lines. So one thing we could do is we could say necessarily, well, if it's an inconsistent system, first of all, these lines or these constraints never collide. The graphs of the constraints never collide. They never share a common xy as a solution simultaneously. So one note that we might want to write in here is this. We say same slope, or at least parallel. They're parallels, double consonant L there. And if we were to sketch a diagram of this, it'd be something to this effect. They would never collide. So now our last case here is very, very similar to the first one in that you can see that the left side of this equation is very identical to the left side of the second equation, but also this, they're pretty much the same equation. Like if we were to necessarily triple the top equation, you would end up with a bottom one. In this case, since we're going to solve using the elimination method here, I'm going to negative triple, but we end up with this. We get 6x minus 9y is equal to negative 18, which is identical to the bottom equation here. So not only will we drop out our variables on the left here and get 0, but we also get 0 on the right, which is totally valid. This is a valid statement like always. So we say true. Awesome, man. So we say that this is consistent. Now, this is considered a consistent system, but a consistent dependent system. So we're going to talk about the difference between independent and dependent. But consistent because it has a solution. This just means solution. There exists at least one solution. Or solutions. And in this case also, we say if we were to graph these, well, if they're the same line, you're going to end up with a situation where you got one line right on top of the other line. So it's, you know, if it's a question of, well, what solution points do they share them all. So we refer to this as dependent because, you know, you can think of one line depends upon the other line. They depend upon each other. They are the same person. Whereas when we have consistent independent, I always kind of think of this as two lines up here on the top left. We say two lines that collide once, but for the rest of the part, you know, for the rest of their x values, they are independent of one another. So just real quick, we'll take a look at the graph of these two equations here. If we were to get this one out of here, and we said, all right, so we have 6x minus 9y equal to negative 18. I believe it was negative 18, or maybe it was 18. Possibly negative 18. We'll change this here. So negative 18. See if I can't get my equation right here. 2x minus 3y equals, I've got this. Let's take a look here. Infinitely. Negative 6x, I've got it written down here, plus 9y equals 18. There they are. And then, believe it or not, this is actually both of the equations right on top of one another. So again, we say graphically speaking, it's consistent dependent or infinitely many solutions if they're on top of each other. But algebraically speaking, you end up with a system that has no variables left and you have a valid statement left over. So cheers.